Hi, so today we'll see a geometrical property of set of rational number, or you can say the topological property of set of rational number. So by solving this question, so here it is. So if we take the set A is the collection of positive rational numbers such that whose square less than 2. So then we saw that it is a non-empty bounded above subset of Q, but this set has no supremum inside Q. We'll prove it. So firstly, we have to check two things here. Firstly, we have to check non-empty. Then we have to check it is bounded above inside Q. So it is a upper bound in Q. And then we check that the supremum, the concept of supremum not exist of this set inside Q. So let's do one by one. So basically in my proof, what I will use here, basically I will prove in my proof, I will use that Q plus dot is a complete order field. So recall, just if you have no idea about the complete order field, so I mean the order field, that what is order field, so then you can go back to, you can go to the basic book, then you can check the definition. So recall Q plus dot less than is an order field. So let me tell you what I meaning by order field. So order field mean under plus and dot it is a field, and there is a the order property less than, which is actually in not independent order relation. That there is a relation between plus and less than, and multiplication and less than. Of course, yeah. So this is the order field. So there is a definition. You can check it is from any book. So, but in my proof, I will use this fact that Q plus dot less than is order field. All right. So before prove this, so let me, we can easily do one part. So two part, first part and second part. So I'm writing the first part. So I'm writing the first part, that it is non-empty. The set is non-empty. So how prove? So see, so to check some set is non-empty, you have to guarantee that there is an element inside the set. So clearly it is, one, we know it is a positive rational number, and if you take 1 square, then it will be what? 1 into 1, so nothing but 1. This is less than 2. So what we are getting? 1 belongs to A. So we are getting A is a non-empty set, right? So the first part. Now we have to check it is a bounded above subset. So this means inside Q. So this means this set has a upper bound in Q. So we have to find a rational number such that that number will be upper bound of this set. So I'm going to the second part. So to prove the second part, see, we start with the element. So then we can guess what will be the upper bound. So let we take element small a belongs to the set A. We took then a square is less than 2, because this is from the definition of the set A. Now we know 2 less than 4, so immediately we can write this. So this implies a square less than 4. So now what we can do, both side we can take here a square. Now here important thing that I'm writing here, that if x square less than y square, then we can say here both side, the absolute value will be less than absolute value of this side. It is if and only. This is very important. You can check in any order field. This is true, right? So now this is less than 2. So what we are getting, if we take a from A, then the A is less than 2. So we are getting 2 is an upper bound. 2 is a rational number, is an upper bound of the set A inside Q. One thing is clear, that any rational number which are greater than 2 also are the upper bound of the set A, right? Okay. Now the problem here that we will check the third part, that this set has no supremum inside the set Q. So how to prove? So basically, so before do the third part, let me recall some fact of rational number. Analytic, you can say the topological fact. All right. So let me here just a few concept, very important concept. I'm going to discuss here. You can say the Archimedean property of inside the rational number, right? So what I'm trying to tell you here basically that if this is the statement, if x is any positive rational number, then there exists a natural number n belongs to, okay, n such that you know what, the x always less than k. So it is, the proof is very easy, you can prove it. So but so let me tell you how you prove this type of thing. So basically here the proof, so the proof of the statement. So since x is a positive rational number, so x equal to what, x equal to p by q for some p and q, of course the natural number. Okay, because x is a positive rational number, so both quantity will be, must be positive, right? Okay, now so what, now q is a natural number, so then this imply what, q is greater equal to 1. So then this imply both side we can multiply by x q greater equal to x, right? Now see, x q mean what, from here x q mean p, so p greater equal to x. Now then this imply p plus 1, it is strictly greater than p and p greater equal to x. So we are getting that p plus 1 is strictly greater than x. So we can take k equals to p plus 1, which is a natural number, such that this k is greater than x. Exactly we want this, right? So in the reverse way, if you write, you can write x less than k. So if you take any positive rational number, we immediately we can find a natural number k such that x less than k. It is normal from the the distribution of rational number on the real line. So if you take here any rational number, you can find here a natural number k which is greater than x, because the set of natural number is unbounded with respect to the standard matrix, or you can say the standard distance function. That's why this is true. Now if you change the distance, so then it will not be true. So in different kind of situation there. But yeah, this is very important statement that we are going to use here in the proof. All right, so now let's move to the proof. So now the proof is here. The proof of the, this is called the something called, let me write here the third part. We will prove this set has no supremum in the set of rational number. So how we prove? We will prove, there are two ways to prove basically. Either direct method, you can explicitly prove, or indirect method means contradiction way you can prove. So if possible, let that if possible, let supremum of a belongs to exist and it is a rational. So for convenience, let gives this name. Let's say alpha is the supremum of a, right? So then what here, alpha. Okay, all right. So yeah, clear. So this is fine. Now then alpha is of course greater equal to 1. Why? Since 1 belongs to the set A, and A, alpha is a upper bound, and supremum mean the least upper bound of A, is upper bound of A, upper bound of A. So alpha is greater equal to 1. This is very important, alpha greater equal to 1. Some place I'm going to use this in some place, right? So basically in the proof, unknown theory, how you prove. So basically here what we are trying to do without knowing the concept of square root of 2. We are trying to understand. We are trying to understand that, this supremum is nothing but the definition of square root of 2, and we already know the square root of 2 not exist in the rational number, but without define the concept of real number inside q, we are trying to check that this set has no supremum inside. So that's why little bit, you have to think in a deep way. You have to prove this theorem from the property of rational number, so that I'm going to do here. All right, so of course, clearly alpha, if alpha, we assume that alpha rational number, so clearly then alpha square also a rational number. Now one and only one of must hold, one and only of one and only one of this 2 less than alpha square equal to 2, and alpha square less than 2 must hold. This is from the order property of the set of rational number. This is sometimes called the law of trichotomy. If you take two number from a order field, of course, then any, if and both number are not equal, two numbers are not equal, then either one is greater than to the second one, right? So this is very important property. So now what we do here, we'll check that none of the relation hold, then we get contradiction. So first assume that, suppose you know what, this is hold. So if possible, let, so suppose we are assuming that alpha square is less than 2, right? So now the proof how you make contradiction. So basically, see what we are doing. This is your this is your square root of 2 someplace. Now alpha square root less than 2 mean what? Alpha less than square root of 2, so alpha will be here someplace. Okay, so see because we are not actually, we cannot take that square root of 2 will be the supremum, but you can take it when you are proving this theory. You can take it is supremum is this, then you can get an idea how you make a contradiction. So see what happened, you can find out here some number, you know what, that if you can find out some number here, then what happened that basically, this number will be, see, if alpha is not coincident with square root of 2, then in between there is a number, rational number you can find, that will make here guaranteed that there exists such. Then this means that number is appear, and that is in the set A. Then what we get? We get alpha, we get a contradiction because alpha is a supremum. So that I'm trying to do. So now see one thing that, let me tell you the dynamical system. So you have x here, and you want to move from, this direction, from this side to this side. So how you move? So what you can do, basically, you can take here x, then you can take here x plus 1 by 2. In general, you can take here x plus 1 by n. So if you take n tend to infinity, then this number actually move towards x. So that I'm going to use here. So how? So we'll find such some n. So to find out some n, do backward process. So now what I'm trying to tell you, alpha plus 1 by n. This is a rational number, no doubt, that whole square. Let me find. It is n any natural number. We guaranteed it what it will be. So this is nothing but alpha square plus 2 alpha divided by n plus 1 by n square. Now see one thing here that, that 1 by n square, this is this 1 by n square less than 1 by n. So this whole quantity is less than alpha square plus 2 alpha by n plus 1 by n. Why? Because 1 by n square is less than 1 by n. So that's why it is true. So now see one thing, this is, so we are getting that alpha plus 1 by n, that whole square is less than this. So now see, this is what? This is basically alpha square plus 2 alpha plus 1 by n. So we are getting that alpha plus 1 by n, this whole square is less than. alpha square plus 2 alpha plus 1 divided by n. See, here one thing that, we have this inequality, and this is true for all natural number. All n belongs to n, right? Okay. Now see, if we can make this is less than 2. So this is little bit here I am doing. So I come back to here, star called. So alpha square plus 2 alpha plus 1 by n less than 2. We want to find such n exist or not. So this is equivalent to saying what? This is equivalent to saying that here, basically, if this is less than 2, then 2 alpha plus 1 divided by n less than 2 minus alpha square. This is equivalent. And this is also equivalent to saying 1 by n less than 2 minus alpha square by 2 alpha plus 1. Okay. And this is equivalent to saying that you can say that 2 alpha plus 1 by 2 minus alpha square is less than n. So now the question, such n exist or not? Okay. So now go back to this statement as I state here that, let me write down where I did it. So basically, where it was, yeah, I start from here that, if you take any positive rational number, then you can find out a natural number case such that this is true. I'm going to use this basically. So I have to take this positive rational number. So clearly 2 alpha plus 1 by, 2 minus alpha square is a positive rational number. Why? Because since alpha get are equal to 1, so 2 alpha plus 1 is positive, right? And you know what? 2 greater than alpha square by our assumption. So this implies 2 minus alpha square also positive. The ratio of two positive number is also a positive. So this is a positive rational number. So there exists k natural number. Of course, we can guarantee such exists such that 2 alpha plus 1 by 2 minus alpha square is less than k. So now this we can write 1 by k is less than 2 minus alpha square divided by 2 alpha plus 1. Now look at this backward process. Just apply the backward process from here. This is now what you get. So you will get, we are getting that this is basically less than 2. So this is true by star. So what we can say here that, 2 alpha plus 1 by k, 2 alpha plus 1 by k, this is what? This is less than 2 minus alpha square, right? Okay, now what, this is alpha square, you can put this side. So alpha square plus 2 alpha plus 1 by k, this is less than 2. So the such k exist. Now by look at this, star tell us that this is true for all natural number n, and star double star tell that there is such k. So by star and, double star, we get what we are getting here basically that, alpha plus 1 by k less than 2. Alpha plus 1 by k is less than 2. Why? Because see, this is less than 2, and this quantity less than this, where I am taking n equal to k. So therefore this, so okay, so I'm getting here that, this quantity alpha plus 1 by k whole square is less than 2. So this imply alpha is a positive rational number. Alpha plus 1 by k is a positive rational number, no doubt, because alpha positive, 1 by k positive, sum positive, and sum of two rational number rational, so rational, and whole square less than 2. So this is in A, right? So what we are getting that, so we get an element alpha plus 1 by k in A, where clearly alpha plus 1 by k greater than alpha, which is not possible. Not possible. Why? Because alpha is the supremum of the set A, our assumption. So we are getting that, alpha square is less than 2 is not possible. Okay, now we'll prove that. Now let's consider suppose 2 less than alpha square, right? So suppose 2 less than alpha square. So now how we prove? So now we are here square root of 2 and now alpha is here. Now see, we will find out some element here which will be a upper bound of the set A. Okay, so again we start from this direction. If you try to move, we'll start like this: alpha minus 1 by n. So alpha minus 1 by n, that whole square equal to what? Alpha square minus 2 alpha divided by n plus 1 by n square, right? So this is clearly greater than of alpha square minus 2 alpha by n. So what we are getting? Alpha minus 1 by 2. This whole square greater than alpha square minus 2 alpha by n. Now what we are trying to do here basically that see, this process that alpha square minus 2 alpha by n greater than 2 imply what? This will imply alpha square minus 2 greater than 2 alpha divided by n. So this is equivalent, both are equivalent. You know what? This is equivalent to alpha square minus 2 divided by alpha. All right, so 2 alpha greater than 1 by n. So basically I am getting here that n greater than 2 alpha by alpha square minus 2. This is, so this is true. This is called, let's say, 1 for all natural number. This is true. Now what we are doing, suppose we want to find a natural number n such that this quantity is greater than 2, so something like this. So this hold, and now we have to guarantee that such n exists. Again, by that theorem I use already here, this theorem that x is a positive rational number, then such k exists. Again we can use here that property. So by so I'm going to by, so clearly there exist I called again I called k belongs to natural number such that k is greater than 2 alpha minus, you know what, this is alpha square minus 2. So alpha square minus 2. Okay, so now this is 2. So now what you can do that using 1, this is called 2 by 1 and 2, we get what we get by 1 and 2. If you use 1 and 2 in 1, we put 1 by alpha minus 1 by k whole square. We know this is what, this is greater than alpha square minus 2 alpha by k. And now by 1, what is this, is greater than alpha square. Okay, now all right, so this alpha square minus 2 alpha by k, alpha square minus 2 alpha by k, we know what, this is greater than 2, right? Because from here we can, if we use the backward process, we start from here, then we move here, so then here, then we get here this for such k. So we are getting this. So what we are getting, we are getting alpha minus 1k whole square is greater than 2. So this imply alpha minus 1k whole square greater than x square if x belong to a. Why? Because x belong to a imply x square less than 2 and 2 is this greater than. Now see what happened, alpha minus 1 by k absolute value is greater than absolute value of x. Both are positive. X positive, alpha minus 1 k is positive. Why? Because I'm starting with that when I wrote here that alpha is a number which is greater equal to 1. If alpha is a number which is greater equal to 1, then what happened, alpha is greater equal to 1 and this is natural number. So 1 by k is a number less than 1. So alpha is greater than 1 by k less than 1. So difference is positive. So you can remove the absolute value symbol. So alpha minus 1 by k is greater than x. This is true for all x belong to a. So this implies what? This implies what? Alpha minus 1 by k is an upper bound of the set A, which is not possible. Why? Which is not possible because you know what? Alpha is the supremum of a least upper bound and alpha minus 1 by k less than alpha. So that's why it is not possible. So such, you know, such so what we are getting, so we are getting that alpha 2 greater than alpha square, and this is not possible. So so far we get that alpha square less than 2 and 2 less than alpha square not possible. Now only there is only one possibility, alpha square equal to 2. So now this is, we already know this. So this is, you can try that. We know there does not exist x belong to rational number such that x square equal to 2 hold. So alpha square equal to 2 not possible because alpha was a rational number by our assumption. So you know what, if you consider alpha is a rational number, the supremum of this set is a rational number, then what we are getting that then we have to satisfy one, and must be one condition, either alpha square equal to 2 or 2 less than alpha square or alpha square less than 2, but none of the relation hold. So therefore our assumption alpha is a rational number, or that is supremum of the set is a rational number, this assumption is totally wrong. So since it is totally wrong, so we get a contradiction. So therefore, this set has no supremum inside Q, but it is non-empty bounded above, but it is a no supremum inside Q. So Q, the set rational number, is okay, no problem. Geometrically, it will give a distance. So if you take the real line, then basically, so okay, not R. So if you take this line, say, and here you put origin, so every rational number you can think as a length, x equal to p by q. Then you can think it is a length. If x is positive, it will give a point in the right hand side of origin, and if negative, it will give a point on the in the left hand side of here. So x less than 0 and greater than 0. So now still there is a problem that so for corresponding every rational number you are getting a point on the real line, but those rational number are not enough to fill the all length or all point on the real line. So therefore it's a problem. So we have to so the problem because of this kind of situation not true inside the set of rational number, non-empty bounded above subset has no supremum. So we have to extend the set of rational number, and this motivate us to define the set of rational real number, so which will be a complete order field. And it is a theorem that there is a unique complete order field which contain Q as a subfield. See you in the next video. That, thank you so much.